This set of slides is an introduction to risk aversion using the Kelly Criterion. It was developed for the GCAGS, or the Gulf Coast Society of Geological Societies. It's going to be presented in September in 2015 at that meeting. If you would like a copy of the PowerPoint slides or the Excel file that I'm going to be referring to, you can go to the site that's listed here on the home page. What we're trying to determine is how to allocate money between projects that we hope to make an investment in. Usually these projects have uncertainty. We don't know exactly how much reward or how much cost, and usually they have probabilities. That's the chance they will actually be successful. We need to document that information before we can go forward. In this simple example, I'm going to assume that we're trying to make a decision between two games. Now, in order to play those games, we're going to need some money. So I'm going to assume that we have about $100 available to play the games. Now, we can choose to spend that money or not, and we can wait and find maybe better games in the future. So think of that as kind of your pocket money. You can call it your stake or your capital available, or some people even call it your risk tolerance, or the amount of money that you're willing to use. Once we've defined the amount of money that we have available, now let's take a look at the games. You're going to be able to make a choice between these games. You can take all, or part, or none of either game. That means I can take 100% of the game, I can take 50% of the game, I can take 10% of the game, or I can take none of it whatsoever. The only thing we can't do is take more than 100% of the game. There's no 150%, for instance, of game one. That's not necessarily true in all investments that you make. For instance, if you decide to buy shares of Apple stock, you can actually buy 2 shares or 3 shares, whereas an oil and gas drilling venture, you can only really drill a well once. So let's look at these, investigate these options. Whenever we have options, we always have to start by quantifying what the cost is going to be, how much gain or how much we hope to receive if we acquire this opportunity, and then finally what the chance or probability of success is going to be for that opportunity. And we've already defined what capital we have available. So first of all, your cost, how much are you willing to pay to play this particular game? Usually that cost occurs first before you acquire any results. Your gain is how much you will get if you actually are successful with this venture. Your chance is the probability this venture will be successful. So here are the numbers we're going to work with. With regard to the cost, the first game takes $70 to play the game, as does the second. The gain is going to be $80 if you play the first game, and it's going to be $100 if you play the second. The chance of success for the first game is 100%. The chance of success for the second game is 80%. So for instance, if we play that first game, there's a 100% chance you'll acquire $80. You spend $70. Sounds like a pretty obviously good game to play. We make $10 every time we play the game. The other game, unfortunately, has some risk associated with it, or chance of loss. The risk is that there's a 20% chance you will not acquire anything. So let's look at game number 2. Once again, we pay $70, but this time we have an 80% chance of acquiring $100 and a 20% chance of getting nothing, therefore losing our $70. And we have the capital available, as we mentioned, of $100. The first thing I like to calculate when I'm presented with an opportunity like this is what is called the present value. That's the today equivalent dollars of all the revenues that we're going to be receiving. Usually revenues come in period after period, year after year, month after month, day after day, and they all need to be converted to today's dollars. We also have the expected value. The expected value is the average return considering both the possibility of winning or losing. Technically, it's called the probability weighted average of all possible outcomes. So the present value, the total of all our future gains converted to today's equivalent dollars after we subtract the costs associated with them. and this must be a positive value in order to consider it a possible investment. The present value is negative. In other words, we're going to lose money. It's not really an investment. Now, we might buy things or acquire things that have negative present values. An example of that is buying insurance on your automobile. It doesn't have a positive expected present value because it's nothing but an expense, but it's necessary to protect from unforeseen future circumstances. Now, the expected value, once again, is the probability weighted average of all possible outcomes. We really only have two outcomes here, success and failure. So it's the probability weighted or the chance weighted average of those two outcomes. Now, if the EV is positive, it's an investment potential. If the EV is negative, it's called a gamble. And I'm going to be considering this something to avoid in this set of slides. Now, if you're a gambler and you like to participate in risky ventures like lotteries or gambling at a casino in Las Vegas, these have negative expected values, and in the long run, you would expect to make money. Now, you might get lucky in the short run and walk out with some profit, but in the long run, you're expected to lose. Those are different types of investments, and I'm not going to be pursuing that at this time. So let's continue to investigate these two options by calculating the present value. As we said, game number one, we acquired, the gain is 80, the cost is 70, so therefore the present value is $10. The game two, the gain is $100, the cost is 70, so the present value is $3. Now, with respect to the expected value, the little formula off to the right, expected value is P sub S times G minus C. That's a simplification in order to avoid addressing the cost twice. Normally, the expected value, as I said, is the probability weighted average of the two outcomes. And this obviously is not the probability weighted average of two outcomes. The only probability weighting we have is on the gain. So I've really taken the original formula, which is P sub S, or chance of success, times the gain minus the cost, plus the probability of failure, or 1 minus P sub S, times minus the cost, and then combine those all together. Now, if you notice, minus the cost occur twice in the formula, one associated with P sub S and one associated with 1 minus P sub S. In this formula, I've just combined those together to be 100% of the cost. So, the expected value for game number one is $10. The expected value for game number two is also $10. So now we have enough information to actually start contributing to the analysis of the risk aversion. I'm going to use a technique called Kelly Criterion. It's been available since 1956. John Kelly, who worked for Bell Labs at the time, published this method while investigating the impact of noise during the transmission of information. Obviously, Bell Labs is very interested in effective communication using either wireless or wire transmission. He was investigating the problem that we have in understanding the clear communication if, in fact, it's what they call a noisy channel or some background static. Now, in the process, he came across this algorithm that he's proposing, and he used as an example in the paper going to a racetrack and betting on a horse. And so afterwards, this paper became famous amongst gamblers for trying to decide how much to bet on a particular horse at a game. It's also very useful for trying to figure out how much of a particular project we should consider when making an investment. So far we know both the present values and the EVs are positive, and the EVs are, as it turns out, both identical for the two games. In order to calculate the Kelly Criterion, which I'm referring to as K here, all we need to know is the EV divided by the PV. So since the EV of the first game is $10 and the present value of the first game is $10, the answer comes out to 100%. For game 2, the EV is $10 and the present value is $30. So the ratio is 33%. Now I'm going to talk about how to utilize both of these numbers that we've just calculated. The Kelly Criterion is designed to tell you how much of your money available you should consider investing in an investment of this nature. Now remember, game number 1 had no uncertainty, no risk. We were simply going to acquire $10 by spending $70 to acquire $80. So what the Kelly Criterion answer is 100%, or it's telling you that you should use up to 100% of your monies available to participate in this game. Now, as it turns out, our monies are available are $100, which is in excess of what we need to play this game. If we only had $50, it would suggest use all $50 to acquire a percentage of this game. Now, with regard to game number 2, it says that it's 10 divided by 30, or 33%. What it's suggesting is that you should spend up to 33% of your money available to play this type of a game. Now remember, we had $100 available, so this is suggesting that we would spend $33 of it on a game like this and save the rest of it for other games. Why not spend all $70? Because there's a significant chance, 20%, you could lose most of your money here. So it's trying to protect you from a significant loss. So once again, the Kelly Criterion suggests how much your capital you should spend. In one case, it suggests all of it, or 100%. In the other case, it suggests 33%, or $33. Now, unfortunately, the amount we invest cannot exceed the cost, so we have to adjust those numbers relative to the costs. So now that we've calculated the Kelly criteria, we need to adjust them so that they're appropriate relative to the cost of each venture. I'm going to call this proposed Kelly working interest, or the percent of the project you should consider doing. Now, with regard to game number 1, it says that we should take the expected value divided by the present value to calculate the Kelly criteria, and then simply multiply that times the capital available divided by the cost. For game number 1, the capital available is 100 and the cost is 70, and so that comes out to 143%. Now once again, 143% would work fine if you were betting on horses. You could buy more than one ticket on a particular horse race. It doesn't work for oil and gas drilling. So unfortunately, we have to limit that to 100%. So that's simple. We can just use the Excel formula minimum, MIN. So now the Kelly working interest is equal to the minimum of either 100% or 1, or the formula we just calculated. And the result of that comes out to the lesser of the two, 100%. For the other formula, we don't really need the minimum criteria, but it doesn't hurt to have it there. So once again, it's the minimum either 100% or the result of 10 divided by 30 multiplied by 100 divided by 70, and that comes out to 48%. So what it's proposing is that ideally we should take 100% of the first game and 48% of the second game. So 100% of $70 is $70 for game number 1, and 48% of $70 for game number 2 is $33. It exceeds our total cost by about $3. So I'm just going to adjust that down to $30. So what Kelly Criterion is suggesting is these two games are good investments. We should consider playing the first game and using $70 of our monies available to play that game, and use the remaining $30 to play the other game. Now all of this can be very easily built into an Excel spreadsheet, and as I mentioned, I put that on my website if you were interested in downloading the simple Excel spreadsheet. On the left are the two games that we just referred to, and it shows the Kelly working interest and the cost of those Kelly working interests that it's proposing. On the right, I have developed the third game, called game number 3. Now, game number 3 has a cost of only $25, still has a gain of 100%, but there's only a 40% chance of success, which means there's a 60% chance you can lose your $25. The present value of this game is $75. The expected value is $15. Those are both positive. We're encouraged. So then we do the Kelly criteria, and it says 20%, or it's suggesting that we might want to spend 20% of our dollars available on this game. When we convert that to Kelly working interest, 20% percent of $100 is $20 times $25. So $20 out of $25 is 80%. So we're going to take 80% of that project at a total cost of $20. And game number 2 is $33.30. We can continue to add games until we've allocated all of our money. There's another problem we run into if we have too many games and not enough money. There we have to use a linear program to constrain the investments that we make in each game and limit it to only the very best games. I can review that in a future PowerPoint presentation if you would like.